Ever wonder what keeps a steel mill from just melting into a giant puddle of its own making? Or how a cement kiln doesn't just crumble under heat that's way hotter than volcanic lava? Well, the answer is a class of materials you've probably never even heard of, but they make our entire high-temperature world possible. They're called refractories.
Okay, so let's just frame the problem here. How in the world do you hold something that is 2,700 degrees Fahrenheit? We're talking the temperature of molten steel, without the very thing holding it just melting away. This is the fundamental challenge right at the heart of nearly every major industry we have, from metal and glass to cement. And the answer, it's this fascinating blend of geology and some seriously high-stakes chemistry. So here's what we're going to tackle. We'll look at the industrial infernos these things have to survive in, we'll get a handle on what they actually do, and then we're going to dive into the really clever chemistry that lets them survive. After that, we'll meet the key players in the refractory world and see how engineers pick the perfect armor for the job. Let's get started. All right, first up, why are these materials so absolutely critical? Well, it all comes down to the extreme conditions that basically power our entire civilization. The official definition here gives us a huge clue. See, a refractory isn't just about being heat-proof. It's a non-metallic material that's been specifically engineered to survive a three-pronged attack. We're talking intense heat, aggressive chemical corrosion, and immense physical stress, all happening at temperatures that would literally vaporize most other materials.
So what jobs are these ultimate heat shields actually doing inside a furnace or a kiln? Believe me, it's way more than just being a simple barrier.
They really have four crucial roles. First, and this is the obvious one, they withstand those insane temperatures. Second, they have to put up with a constant chemical assault from molten metal, from gases, and from a really nasty byproduct called slag. Third, they provide the actual structural shape and strength to the furnace lining itself. And finally, they act as insulators, keeping all that valuable heat right where it needs to be, which is absolutely vital for energy efficiency. Okay, now we get to the really clever part. A refractory survival isn't just about brute force heat resistance. It's about playing a very specific and very important chemical match game. You see, in a lot of these processes, the number one enemy isn't even the heat, it's the slag. Just think of slag as this molten, chemically aggressive waste product that floats on top of whatever's being processed. And this slag, it has a very distinct chemical personality. Now, slags are broadly divided into two families. You have acidic slags, which are high in silica, and then you have basic slags, which are high in things like lime and magnesia. Chemically, they are total opposites, and they are both constantly trying to react with and basically dissolve the furnace lining. So, here it is, the crucial point. Engineers fight chemistry with chemistry. To contain an acidic slag, you use an acidic refractory, like one made from silica. To contain a basic slag, you use a basic refractory, like one made from magnesia. If you get this wrong, if you put a basic refractory in an acid environment, it will get eaten away and destroyed, fast. It's all about that chemical compatibility. And this isn't just some vague rule of thumb, it's hard science. As this industry handbook shows, engineers literally calculate the ratio of the basic stuff, like lime, to the acidic stuff, like silica. That simple ratio tells them the slag's personality, and that dictates exactly which type of refractory they have to use to make sure the furnace survives. So you might be thinking, what happens in a really complex environment where the chemistry might be shifting, or you've got both kinds of attacks going on? Well, for that, you need a neutral refractory. Materials like alumina or carbon act like chemical diplomats, totally capable of resisting attacks from both sides of the aisle. So, now that we get the core principle of this chemical warfare, let's meet the main families of materials in the refractory arsenal. Okay, here's a quick look at the heavy hitters. You've got silica brick, that's your acidic champion, and it has this incredible ability to resist heavy loads even when it's screaming hot, right near its melting point. On the basic side, you've got magnesite. It's the absolute go-to for the steel industry, perfect for fighting off those aggressive, lime-rich slags. In the neutral corner, alumina is a true all-rounder, just super versatile. And then there's carbon, which has this really unique property where molten metal doesn't even wet it. The metal just beads up on the surface, which is fantastic for preventing any buildup.
Let's just put a spotlight on that high alumina family for a second, because they are the true workhorses of this world. Their performance scales directly with their purity. The more alumina you have, the higher the temperature they can handle. And this versatility is why you find them absolutely everywhere, from the inside of cement kilns to glass tanks and steel ladles.
So, how does an engineer take all this info and actually make the right choice? Well, it's a systematic process. It's like a multi-factor puzzle they have to solve for every single application. Because that chemical compatibility, as critical as it is just one piece of the puzzle. The final selection is always a careful balance of the thermal, the mechanical, and the chemical demands, all working together.
So here's the engineer's checklist. They start with the chemistry. Is the slag acidic or basic? Then they figure out the maximum temperature. After that, they have to consider thermal cycling. That's rapid heating and cooling, which can cause cracking, a thing called thermal shock. Next, they evaluate mechanical stress, like abrasion from raw materials getting dumped in. Number 5, and this one is crucial, they look at the furnace design. It's not just about the material, but the form it takes. Are they going to use classic bricks? Or maybe a castable material that you pour like concrete, called a monolithic? Or even a mix that gets sprayed on with a gun? The whole lining design is part of the choice. And finally, of course, all of this gets balanced against cost to find the most effective solution for the money.
And to give you a sense of scale, just consider this. Over 70% of all refractories made are consumed by just one sector, the iron and steel industry. That single fact just hammers home how absolutely fundamental these materials are to our entire industrial backbone. So after all this, you might be thinking these materials are just confined to giant, far-off factories. But the truth is, their influence is pretty much everywhere.
The reach of this technology is way wider than you might think. I mean, yes, they line steel converters and cement kilns, but refractory technology is also in the protective heat tiles on space vehicles. It's used in military armor. It's the little ceramic insulator in your car's spark plugs, and it forms the crucibles that are used to melt precious metals for jewelry. Literally everywhere humanity has needed to master fire, refractories are there.
So the next time you look at a glass window, a steel beam, or even a piece of pottery, just take a second. Think about the incredible unseen shields that had to withstand an industrial inferno just so that object could exist. What part of your world was forged in fire, protected by them?